All right, we are back. It is game 2005. That's game physics in the fall 2017 semester, and it's week 4, part 2 of our broadcast. We're talking about 1D motion again. This is part 2 of 1D motion. We left off with this idea of, guys, we left off with this idea of motion diagrams. And remember, we talked about, visualization is important in physics. And what we're trying to talk here is different motion diagrams to describe different kinds of motion, A, B, or C, 3 different types of motion and the effects of it. So velocity, constant velocity, velocity under acceleration in the same direction, velocity, notice that the velocity, the V value, the red line goes smaller and smaller because the acceleration is in the opposite direction, okay? So when we talk about constant velocity, right, notice the images here are equally spaced. That's what the idea is. And we can say that this is a positive velocity because it's moving to the right. Okay? I know that this is, for some of you, like, hey, it's to the right, it's positive. By the way, don't think about physics as right, never wrong. Okay? It's not like you're going into a maze and going, okay, my alpha is in a maze. If I take the right path, I'm not going to get killed by a trap. Okay? It's not like that in physics. Sometimes you get trapped either side. Okay? So, right, it just means the direction. This is where you're moving. Acceleration equals 0. Why? Because the velocity is constant. And if I take a constant velocity, so example would be Vt, right, where V is constant, right? And there is nothing else in the equation. And if I derive acceleration from a constant velocity, I'm going to get nothing, right? It's going to be a constant. It's going to be a 0, right? Because my velocity would be example 5, right? Constant velocity, 5 meters per second. That's a constant velocity. And if I have 5 meters per second, and if I take the derivative of 5, derivative of constant is 0, which means my acceleration is going to be 0. And that's a great test for you guys. You guys did calculus in the first 3 weeks. So that's a great litmus test to figure out if your answer makes sense. Do calculus on a position of velocity acceleration question or integration going backwards. And then you can look at it and go, yeah, that makes sense. Because if I use my derivative, I get a value that makes sense. And I did that when I was doing this the first time around, way back in the day. All right, so here's another situation. So where I have a acceleration and velocity, but in this case, the acceleration and the velocity are in the same direction. Notice that the velocity is increasing, and we show positive acceleration because we're moving towards the right. Acceleration is positive, right? In this particular case, though, the next case, we have positive velocity, right? But then we have negative acceleration, which causes our velocity to stop being constant. Our velocity is actually changing. It's going slowly, slowly. It's decreasing, right? So we have a positive velocity on the right side. We do have velocity, but the velocity is decreasing. And when I talk about acceleration, it's the rate of change. If I have a negative rate of change, which means I have a negative acceleration. It means acceleration is pointing in the other direction. Okay? Very, very simple here. All right, so again, we're representing motion of a particle under a constant acceleration for the most part, because once we start talking about things in acceleration that's changing, we can't use regular kinematics for that. We have to use other kinds of equations. The equations that I'm going to be giving you are all most likely, for the most part, going to be with constant acceleration or constant velocity. So we can use our kinematic equations. And what are those kinematic equations? The ones that we move in one direction or one dimensional, and also some of it works with 2 dimensions, right? What are these things? Well, the first one is this one. The first kinematic equation you need to know is V final on the x direction, right? So the velocity in the x direction, the final velocity, is equal to the initial velocity, right? Plus the acceleration in the x direction times the time. So in this particular case, if I had an acceleration of 0, right, then my final velocity and my initial velocity would be the same, right, if I didn't have any acceleration. And that means I have constant velocity, right? If my acceleration, let's plug in some values here. Let's say, for example, I have an acceleration, a velocity of 5 and an acceleration of 3. What is my final velocity? And if time is Let's write this out, right? So what am I saying here? I'm saying if I plug in, let some values mean something, right? So I'm going to put in some values here so you guys can work it out. Let t equals to 2. Let's suppose t or 2. My velocity initial, we'll say vxi, I can't draw it right now, is equal, my initial velocity is 5, right? And my acceleration, right, across the x-axis is 3. What is my final velocity? Then my final velocity across the x-axis is, what is it? How do I figure that out? Plug it in. It's just substitution, right? So I take, remember, mathematics, I work the multiplication first. So I take the acceleration, which is 3 times 2, which is 6, right? Plus the 5. So my final velocity is 11. Okay? It's pretty simple. And meters per second. Always meters per second. Or unless I say something like on an assignment, pixels per frame. Meters per second, right? Some kind of units that I give you. Okay? Yes.
So for the equation for t, can it also be changing time?
Right now, no. It's not. This is not the kinematic equation we're talking about. Remember, we're assuming that time is equal starting at 0. So it assumes time is t initial is 0 and t final is some other value of t. Right? Kinematic equations are like that. They're very simple. You try and map out a simple relationship. Right? Simple motion. So this is a kinematic equation number 1. Right? By the way, we're going to refer to these kinematic equations in next week when we actually add on to them to get 2D motion. All right, so let's talk about kinematic equation number 2. I want to find constant acceleration, right? My constant acceleration, right? Or I want to find my average velocity. Here's my average velocity. So velocity on the x-axis, average, is equal to my initial velocity plus my final velocity divided by 2. That's average velocity, right? The average velocity, right, is what I'm getting here, average velocity, right? So I'm taking the 2 values and dividing by 2. I have 2 values. So let's say, for example, my initial velocity was 3, and then my final velocity was 5. So 3 plus 5 is 8 divided by 2. That means my average velocity is 4. That's all it is. Take your final velocity and your initial velocity, add them together, divided by 2, and that's your average velocity. Okay, like any other average, very simple. Equation number 3, right, where I have a constant acceleration, right, as an example. And what this does for me is this gives you the position of the particle in terms of time and velocities. So I have a couple of equations here all in one. On the left-hand side, I'm looking for the final position, right? Final x position, right? I take my initial position plus an average velocity multiplied by time, right? And then I get my final position, right? Or you could take your initial, position plus half of your velocity final plus your velocity initial, which is really just taking this apart. If I take Vx average, that is final velocity plus initial velocity divided by 2. I'm just taking this and expanding it over here times time. And sometimes we need to do this because of the kind of question we're getting. We might say something like this. You know, your velocity starts off at 3 and then it ends up at 5, you know, in 2 seconds, right? Then what is your final position if your initial position was at the origin, right? Then you just plug in those numbers. The initial position means origin means 0. So my x initial will be 0. And then I would take the second part, the second way of looking at the equation. So 3 plus 5 would be 8 divided by 2 is 4, right? Times t, 2 seconds, right? I said 2 seconds, so that'll be 8. So it'd be 8 meters per second, right? 8 meters would be the average, or would be the position, the final position over this equation. We'll talk about this more in tutorial. All right, kinematic equation number 4. When I want to find acceleration, by the way, ladies and gentlemen, we're going to be using this a lot, especially in 2D motion, right? So let's think about this. My final position is equal to my initial position plus my initial velocity times time plus half of my acceleration times time squared. And the way I usually talk about this is P naught in terms of position, initial position, P naught plus V naught T plus 1/2 AT squared, right? Where A is acceleration. If A was gravity, this could determine a parabola, right? That's what it would look like. And if I looked at this for this stuff, let's just try and map this out really quickly. I don't have a lot of time. Let's try and map this out with Desmos, right? So here's Desmos. And if I want to put those values in, so if I say that my final position, if I express it in a new expression here, so if I say that my final position, y, right, as an example, is equal to initial position, x, right, let's say, my initial position plus whatever it is, v t, so v times t, we'll calculate this in a second, plus 1/2 a, and then if I do t squared, I put this in there. Now I need values for all this stuff, right? I'm looking at the final position. If I have v, let's make a slider for v, right? And if I have t, I make a slider for t. And if I have a, I have a graph, right? So let's say that a is gravity, right? So we'll say that a is a negative 9.8 meters per second squared, right? 9.8, okay? And if I say t is 2, right? And my velocity, my initial velocity is 3, you can see that I'm going to get a position graph, right? That's what this thing is.
We're going to use 9.8 for gravity.
Negative 9.8 meters per second squared, right? Does that make sense? So you can see that that's the graph I'm getting. So at any point on the on any collinear point here, right, on the line, any point on the line, I can see that this equation is going to tell me at any point t, right, what the what my line is going to look like. Okay, so very interesting way of looking at it. If you map this out differently, you can also look at it in terms of x, right, where you can put x final and x initial. You can actually put the exact equation in here in Desmos. That's why I really like this program online. Kudos to the people that made it. Okay, so that's what this equation. One of the most popular equations. It describes a parabola most of the time because its final position, the displacement. That's what we're talking about. So I want to find the displacement of an object, a cannon that I'm firing up in the air, as an example, or I'm throwing a rock. This is even easier. I'm throwing a rock off a cliff, right, with a certain velocity. My initial velocity is, there's a certain velocity in the x direction, right? And this is where we're going to talk about next week, right? And I have an initial position, right, on top of the cliff, and then I'm going to describe motion of a particle falling. Okay, kinematic equation number 5. Now, it's the same equation, right, for acceleration, but notice that there isn't any time value. This is interesting because sometimes we don't have the time value. We don't know how much time has elapsed. And we want to be able to figure out acceleration or velocity without a time, right? And if you look at this equation, we're saying, well, v squared, the final velocity squared, is equal to the initial velocity squared plus 2 times the acceleration on the x-axis times the initial position or the final position minus the initial position. Okay? So if you move things around, and every time whenever you see a square somewhere, v squared, chances are that means there's a couple of answers, right? Chances are, if I want to find what v is, I might have a negative answer and a positive answer. And there is the classic quadratic equation. Anyone remember what that is? How about, is that it? Over?
By 40.
How about Hercules? Hercules, what's a quadratic equation? Come on, you're the master.
A plus b squared.
A squared plus b squared is equal to c squared. Sorry. Ax squared plus bx plus c. And if I'm solving for, right? If I look at the quadratic equation, I put it in a different form. It's minus b plus or minus the square root of b squared minus 4ac over 2a, right? And if you look at that, if you want to look at that, what that is, we may have to use that sometimes to solve things. So if I look at the quadratic equation, or formula, if you will, see it in different forms, and I'm going to put it on your cheat sheet as well. I don't see it right away. Let me see, maybe I call it quadratic formula. I could. Quadratic formula. Yeah, there it is. Right, so see if I can bring that a little closer. This is it right here. Right? Minus b plus minus the square root of b squared minus 4ac over 2a. And why is that? Because we have a squared value, and we need to get the square root, right? And remember, you take an equation, and you want to be able to disseminate that equation in different parts, ax squared plus bx plus c. And when you do that, when you have a, b, and c in that quadratic equation, and by the way, this last equation, right, the one we just had, not this one, but this one, if you think about it, right, if we're talking about time, right, ax squared, right, is the last part, right? So if time is x, then ax squared plus bx plus c, right? Notice that this equation here, if I'm solving for time, can be put into this into a quadratic form, right? So I want to know how much time has elapsed when I move from one place to the other. I have to use the quadratic equation, because if I'm using a position function. So if I tell you the final position is 53, and if I tell you the velocity, two other values, if I tell you the velocity is so and so, right, and the time and the acceleration is so and so, as an example, and then I want to know the time, how much time has elapsed. That's a quadratic formula that I'm looking for, right? Yeah.
So you use quadratic equation, so the final velocity is 0?
No, that would make it, well, no, that would, you could still use it. You could still use that. You would use it where the final velocity is 0. Well, let's keep going. All right, so what about when acceleration is 0? When the acceleration is 0, we can say that then v final is equal to v initial, right? It is equal to the velocity over the x, right? Because that means there's no acceleration. Velocity is constant, so therefore v final is equal to v initial, right? And then your final position then is equal to the initial position plus vt. So you chop out that plus 1/2 at squared, right? You don't have that part. That part of the formula goes away because your acceleration is 0. All right. And here are the quadratic equations in summary. There's 1, 2, 3, 4 of them. Will I make you suffer and remember these ones? Absolutely not. You're going to have them on the test. You're going to have them on the cheat sheet, right? You're not going to have to remember this stuff. You just have to remember how to apply them. And sometimes you're going to have to apply more than one, or figure out how to use a quadratic equation to derive the answer, right? All right. So again, slope of the curve is the velocity in this particular case. So here's the position function. Slope of the curve is velocity. Notice that the curve indicates the velocity is changing because I'm getting my velocity has both magnitude and direction. And because the velocity is changing, right, that means there must be acceleration. So when you look at a curve like this, I might ask you, is there any acceleration with this curve if these tangent lines are velocity? And the answer is yes, there would be. How about this? The slope gives the acceleration. Here's the acceleration. It's constant acceleration, right? Why? Because it's a straight line. It doesn't go up and down. Constant acceleration, right? Here's one when the slope is 0. If slope is 0 and we're talking about acceleration, then that means constant acceleration again, right? Constant acceleration, right? Slope is 0 in this particular case because it's not going up and down again. So ways of looking at this. Okay, changing gears a little bit. We're moving into this idea of this dude, Galileo Galilei, right? He's an Italian physicist, mathematician, astronomer. He was one of the fathers of physics, back in the day. He believed he had this idea that one of the people that believed that the Earth went around the sun, as opposed to the older physicists that believed the everything went around the Earth, the geocentric model of the universe. He started believing that, well, everything goes around the sun, the heliocentric model of the universe, right? Which is actually still wrong, right? Because not everything goes around the sun. Everything goes around, right? It goes around the center of the universe. It kind of moves around all over the place. We have the center of the galaxy and the center of the universe, and someplace we have motion kind of moving out from an initial position. But his laws really work well for things like bodies in motion, like the stars and the planets, right? If you think about how they move in an elliptical pattern around the sun, right? Before, we couldn't figure out how to establish things, and the older philosophers would look at things and go, hey, how come it's going back? This idea of retrograde motion, how it's coming back. Well, it describes this ellipse, right? So he kind of formulated the first laws of motion, and Newton took Galileo's work and expanded upon it, which we'll see in next week. All right, so he talked about this idea that we're still talking about 1D motion, but just like we said in the beginning, we have this idea that if I drop something, right, from a height, it's going to move down at a certain acceleration. If I throw it up, then it's going to come down. Whatever you throw up comes back down, right? And if I throw it downwards, right, it's going to have the acceleration due to gravity plus my velocity. So it's actually going to go faster than if I just dropped it, okay? So that we can describe that kind of motion as well. So we normally describe gravity. Some people describe it as in feet per second. What is it in feet per second? Anyone know? 32 feet per second squared, right? And from meters per second, because we're in Canada and in most countries that we use metric, we describe it in approximately 9.8 meters. It's not accurate, actually. What's the accurate version? Does anyone know? It's actually around minus 9.81 meters per second squared, more accurate than 9.8. For us, for what we're doing, I always want you to use 9.8. Minus 9.8. Why is it minus? Acceleration is a vector, and it's pointing downwards. Therefore, it's a negative acceleration, right? Because it's pointing down. If it was going upwards, if I was accelerating something upwards like a rocket, it may have positive acceleration going upwards, right? You're going to ask a question.
Yeah, you said if you drop an object, you have gravity and then additional velocity.
If I throw it.
Yeah.
If I throw it. If I drop it, if I just drop an object, right, it's just gravity, right? And actually, there's a video I'll show you guys maybe during tutorial where recently one of the astronauts that originally went on the moon, I know people believe that the moon was a farce and all this kind of stuff and it didn't exist, but actually he had original footage. I know it's all this conspiracy theory stuff, right? Actual footage of him taking a rock, I believe, and a feather and dropping it on the moonscape at the same time, and how it falls at the exact same time, because it doesn't matter the mass of an object. When we get to Newtonian physics, we're going to talk about this a little bit more. They drop at the same time. It's not mass dependent, it's mass independent, right? So every object accelerates approximately at 9.8 meters per second towards the Earth. Now this changes because of latitude, right? So the higher up I am, the farther away I am from the center of the Earth, it's going to slightly be changed. And the reason for this is because our center of mass, depending on where the center of mass is, there's less gravity as you go farther away from it, because you're further away, it has less of an effect. It's almost like if I was using the Force in Star Wars and you're farther away and I was like Darth Vader, I'm making a deeper voice here, I couldn't control you so far away as if you're right next to me, right? I would like be able to do the pinch on your neck, no problem from here, right? But if you have the chokehold, it would be totally no problem. But from far away, if I was going to try and do with Emma, maybe she's too far away, right? Yeah, I know. But that's the way it is for gravity. Gravity, it works better when it's closer together, right? And actually, gravity is the thing that causes pressure in the Earth, right? Especially when it comes to objects that are inside the water. The reason why we feel so much pressure when we're inside the water as we go towards the bottom of a lake is because pressure increases as we come lower and closer to the bottom of an object, right? Because the deeper we are inside the ocean, the more pressure there is because of all the water that's there. Right? We're going to talk about fluid dynamics later on in the course, as well as the gravity is actually stronger too. All right, so we're going to use an italicized G to denote gravity, right? That's just something we're going to do. The idea that the acceleration in the y direction, so we're talking about the y, not the x, right? We're not talking about 2D yet. In the y direction is a negative G, because remember we talked about gravity as being an acceleration. An acceleration has to have distance and direction, right? So, or magnitude and direction. And magnitude might be a negative value because we're moving in the negative direction down towards the Earth, right? So it's always negative 9.8 meters per second squared. Also, we're going to neglect in this course, for the most part, unless I say otherwise, we're going to neglect air resistance. Why is that? Because if I'm jumping out of a plane and if I spread out like this, it's going to take longer for me to fall than if I gather myself together, right? Gathering myself together means I have less space. If I space out or if I decrease the pressure, right? Air pressure itself is trying to buoy me up, because as I increase my speed, the air pressure itself is kind of coming against me, right? Less resistance. But if I kind of gather myself together, that means it's going to be less of an effect because of the shape that I'm putting myself in. And so if you notice some of those, if anyone ever watched 007 back in the day, maybe not, maybe if you're someone who likes James Bond, every time he's flying, or even some of those crazy competitive divers, they kind of put themselves into a shape where they can come at you. The reason why, they're making themselves aerodynamic so they can reduce the effect of air resistance or direct themselves like a wing of a plane, right? So it's kind of very interesting. You have a question? Anyone have a question?
Yeah. So
Yeah.
about that, so if you're descending, then eventually you'll be at a constant.
Yes, it's called terminal velocity. And what's terminal velocity? Approximately 150 meters per second. All right, squared. And that's when things stop. You can't go faster than that because of we talk about things like air resistance and everything else. It can only accelerate you so fast, and to reach terminal velocity, you have to be quite high, right? Later on. So here is an example of an object that's being dropped. Here's your object. It's pretty big. The velocity starts at 0, right? And then our acceleration is negative g, because the gravity is in the negative direction, right? And then up, let's suppose that the upwards direction is positive and the downwards direction is negative, right? Why? Because I'm going to put it on the y-axis, guys. That's what's happening. I'm on the y-axis, and positive is up and downwards is negative, right? And then I'm going to use this idea of y, acceleration in the y direction is a negative g. I'm just dropping it, right? That's all I'm doing. And now here's an object that's thrown downward. Well, guess what? I not only have a negative g value, but my velocity cannot be 0 because I'm actually throwing something down. So if I'm on the top of a cliff and I throw something down with force, right? It's going to be faster than just regular gravity pulling it down if I drop it, right? We're just describing motion here. So that's the second possibility. And the third possibility is where I have something like this. I'm at the top of a cliff or whatever, or someplace, and I'm throwing an object up. It's going to come up, and then it's going to reach a point where the velocity is going to slow down until it's 0, and then it's going to turn around and come back down, and it's going to accelerate in the negative direction towards the ground with a negative 9.8 meters per second squared. Okay, so that's the three possibilities we're talking about here. So if we think about this idea of motion being symmetrical, and most of the times it is, sometimes it's not, right? Then the time up and the time down is approximately equal. So the time I send it up, right, equals pretty much the time that comes down. If you think about this, right? T up is equal to T down. If that's true, then the velocity is equal to the negative, whatever the negative velocity was. Whatever I sent it up with, if I charged it up with, I don't know, I threw it at 5 meters per second somehow. I was that strong. And I threw it up as 5 meters per second, right? Well, then it would have come down at 5 meters per second plus my acceleration. All right, so velocity final would be whatever would be coming down. And here's an example of this. I'm going to kind of zoom in here. It gives you, this is a really good example from the book, all right? So if you look at it, you can see that there's a man, all right, or some kind of human being, it looks like, that's tossing things up, right? He starts off, his initial Y position is 20 meters off the ground, or he's maybe 50 meters off the ground. There's 50 meters, right? His initial V, his velocity, somehow he's throwing up this ball at 20 meters per second. Woohoo! He's a star, right? 20 meters per second, right? So he's throwing this up. It's going to come up until my velocity reaches 0, because it's going to continue to decelerate. Because why? We have motion in different directions. I have a velocity going upwards and a negative acceleration going downwards, right? Which means I'm going to be decelerating. Sorry to use that word. My velocity is decreasing every time tick. Every time the time goes, my velocity is decelerating until it becomes 0, and then it's going to reverse direction and come back down, right? And it's going to continue to accelerate until it passes him, right? So for example, at time equals to about 4.08 seconds, based on these numbers, it's going to pass him, and it's going to at position C, and it's going to keep going until it hits the ground 50 meters below. And notice that what the answer is going to be, if you use your kinematic equations, right, is that you're actually getting a total time of 5.83 seconds. The total distance is negative 50 meters, right? The final velocity is negative 37.1 meters per second, because velocity is a vector, right? Negative 37.1 meters per second. And of course, with acceleration being a constant, negative 9.8 meters per second squared. Yes?
So in the future, will we be using the kinematic equation, like more than one kinematic equation?
We may. Yes, sometimes you need to. And we'll break up a problem into parts, right? All right, so if you notice, the initial velocity at A is positive, and then if you look at each case, it talks about what happens when it comes up and comes down. We did calculus, so some of these kinematic equations work in reverse. You can figure out calculus like we said, and if you look at some of them, if we have our initial position, here's our position, and we want to go backwards, we can find that the velocity comes from position, and that acceleration comes from velocity. That's what happens. So if you look, as you move up the chain here, you can find acceleration from position, like we talked about. And same thing goes from an integration perspective. If we start out with position, we can go the other way and find everything we want. All right, when we solve general problems, I'm going to leave you with this thought. I'm going to talk about the other problems in the tutorial. When we solve general problems, there's 4 stages that I want you to think about things that help students figure out stuff when it comes to physics. I know the guys in the back, you guys are dying. You're like, get me out of here. I don't want to be here. Bear with me for a few more minutes, okay? I swear to God, it's not going to be that bad. 1, we have to figure out how the heck we're going to conceptualize this thing. And what are we going to use? Diagrams. I'm going to use diagrams. I'm going to use graphs. I might use tables. Whatever I have to do to try and figure out what's happening. I'm trying to map it out. This is the real life stuff, right? I'm going to categorize my problem. What kind of problem is this, right? Is it a motion in 1D problem, a motion in 2D problem? And eventually, this is the same problem. The same steps we're going to use in later modules when it comes to physics. And then we're going to analyze it. We're going to say, which one of the equations can I use? Or do I have to use more than one equation here? Do I have to break this problem into parts? That's my analysis. And then I'm going to finalize my equation by turning it into math. I'm going to take my problem, think about it, draw it, categorize it, analyze that thing, and then turn it into math. That makes sense. All right, and I'm not going to talk about this. I just talked about this thing. Each of these steps are labeled here. I'm going to talk about them more in tutorial. I want to get to talking more about some of the problems. Here's a problem example. I want you guys to help me with this problem example, right? So a racing car starts from rest at t is equal to 0. Okay, so time, where t is time, right? And reaches a final speed v at time t, whatever that time is. If the acceleration of the car is constant during this time, which of the following statements are true? So this is a true, false, multiple choice kind of question, right? A, the car travels a distance at a distance vt. Is that true? A distance vt. So remember I said a racing car starts at t is equal to 0 and reaches a final speed of v and a time t. So then the total distance traveled is vt. Is that true? Why? Because it says if the acceleration of the car is constant during this time. That's the key, right? Okay, B, the average speed of the car is v, the velocity, divided by 2. Is that true?
No.
Why is that not true?
Isn't it just B?
The average speed of the car. Speed of the car. Remember I talked about speed and velocity, right? And think about this for a second. And the magnitude of the acceleration of the car is vt, v divided by t. The magnitude of the acceleration. Remember we talked about, here's 600 meters. We take a look at the diagram. We also have some interesting information here. 600 meters, right? So we're going to go from one end to the other, 600 meters, in a specific time, right? And E, none of the statements are true, right? Or A through D is true. Let's try this out. So here's the actual solution. I'm going to post the solution up here. So the initial velocity of the car is v naught, or v0, v to the 0, which is equal to 0. Starts at 0, and the velocity at time t is v. The constant acceleration is therefore given by, remember that kinematic equation, right? When we look at the final velocity minus the initial velocity over the final time minus 0, right? And if you simplify, it's v over t. So that's true. And the average velocity of the car is the initial velocity plus the final velocity divided by 2, which is just v over 2. So that's true. Second one is true too. The distance traveled in time is the change in x, right? Which is equal to the velocity vector times the time, or vt, velocity times time, divided by 2. And it says in the special case where acceleration is 0, and hence, because it's 0, then initial velocity is equal to the final velocity, we see that the statements A, B, and C, and D are all correct, right? So it's all true. Except for the one that says they're not true, E, or whatever it is. So that's an example of something that you might get. You might get something like that. Say, here, is it true or not? True or false? Are these things true or not? Or ABC is true. Yes.
So kinematic equations only work if the acceleration and velocity is constant, right?
Yes. All right, here's another one. The position versus time for a certain particle moving along the x-axis is shown in figure below. Find the average velocity in the time interval A, 0 to 2 seconds, B, 0 to 4 seconds, C, 2 to 4 seconds, D, 4 to 7 seconds, and E, 0 to 8 seconds. How would you figure this out? The reason why I'm not going through the details here is because I'm going to go through the details with you in tutorial, right? We're going to try this out. So if you look at this, so from 0 to 2 seconds, if t is on the x-axis, you can see that it goes from 0 to 10 meters, right? So 0 to 10 meters. Okay, so I've moved 10 meters over 2 seconds. What's the average velocity? 5 meters per second for the first leg. There's different legs of the journey, right? And for each leg, you can find the average velocity based on the total distance traveled, right? Distance initial minus distance final, displacement, whatever, over the total time, right? And then if you add them all together, if you really want to, you can find the average velocity for the entire journey, right? Or the final, and the total distance. What's the total distance traveled? The total displacement is 8, would be a certain amount of displacement. You can figure that out. The total time is 8 seconds. In 8 seconds, it does the entire journey. But what happens here? Look, let's look at the graph for a second. Take a look at this part. So when between time is 4 seconds and time is 7 seconds, what's happening, right? So here's time is 4 seconds. We start off at a constant velocity here, right? And then what's happening is, if you notice, or we're going down, we're moving, my distance is, we're staying the same here, and then suddenly we're moving backwards. We're moving backwards until we move beyond where we first started, in negative territory, right? So we're moving in a positive direction here, right? If you're going to look at it from a velocity perspective. And then we're moving in a negative direction here, which is a negative velocity, moving backwards, right? So the total displacement, right, for this whole thing might be, at the end of the day, positive, because you can see that maybe, because there's positive here, but negative, 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 and a little bit of positive here. So if you add these two vectors, displacement vectors, you might see that the total movement, let's say as an example, is only 0, right? Because it comes back to 0. So the total displacement is 0. but the distance traveled is something totally different. Okay? So something to note here. I've also included the solution here with a lot more numbers. So I say, well, let's take a look. It's the average velocity here is 10 meters minus 0 over 2 seconds minus 0, which is approximately 5 meters per second in this particular case. In the first case, between time is equal to 0 and time is equal to 2. And so on, which we're going to cover. I've put some more questions in here as well, right? So I've got a couple questions that I've answered, right? And there are a few questions, this one, and this one, that I haven't answered. And those are for you to figure out on your own, okay? So please take a look at them, right? See how you can apply them. There's more opportunities for us to check this out. We're going to do more questions. And remember that I'm also going to give you an assignment based on these 4 chapters coming up. So remember, your next test is going to be based on 1D motion, 2D motion, and a bunch of other stuff, right? So it's going to be bigger, and it's going to take more time for us to do it. And it's probably going to be in the second half of the semester because we're sitting at week 4, and we have 4 more weeks of this stuff or 4 or 5 weeks more before I gather enough information to give you another test. Remember, the remaining 2 tests are going to be worth 20% each. Right? So 15 for the first one, which is next week, 20 for the next 2, which is another 40, right? So it's 55%, right? Plus each of your assignments, 3 assignments, right? Worth 15th on each, right? There you go. Any questions around the stuff we've talked about today? All right, so those people going to tutorial later on today, I will go into more detail, and I'll try and do some programming tutorial today and bring up a little bit of Unity. Otherwise, for the rest of you, I'll see you on Thursday.